All right, thank you very much, and thanks to Connor for a great introduction on TOTP as well. So I'm going to be talking in this paper about multi-factor key derivation, and I'm going to set up the problem by first discussing a password management service, which is a typical use case for password-based key derivation today. So typically what you would see in a naive password management implementation would be some kind of authentication server that you send a password to get an authentication token, and then some kind of database that you use the authentication token with in order to retrieve some stored data, stored passwords in this case. And immediately there are two major issues with this naive implementation. The first issue that has been discussed at length already is that passwords are a horrible sole authentication factor, so you don't want that to be your only means of authentication. And secondly, it's that databases, particularly in plain text, are likely to have some kind of vulnerabilities or some ability to be compromised. And so storing these passwords in plain text is also a bad idea. And so in response to this, the typical reaction of a password management service today is to say, well, passwords are insecure, so we're going to add some kind of multi-factor authentication. Maybe we'll add TOTP. And okay, databases could be leaky, so we're going to add password-based key derivation to the system here, where we use your password to derive some symmetric key and then encrypt all of your stored data using that password-derived key. But hold on, there's an obvious issue with this picture, which is that if passwords are so insecure that we need to add multi-factor authentication, then why is password-based key derivation a valid solution to protecting my data in rest? And so the question that this obviously leads to is, can we incorporate all of those multiple authentication factors into the key derivation function itself, such that your data is directly protected by all of the authentication factors that you're using? And that's exactly what we do. We call it the multi-factor key derivation function, or MFKDF. And the basic innovation here is to take all of the authentication factors that users already know and love, such as their SMS, their TOTP code, YubiKey hardware, etc., and incorporate all of that cryptographically into the key derivation process. Now, this is easier said than done because, of course, the way that password-based key derivation works is that you have a relatively static input, like a password, and then you apply a deterministic one-way function to get a static key. But as Connor introduced just a few minutes ago, TOTP is not static. It's changing every few seconds. And how do I apply something to that where I still need to get the correct key as an output if and only if I supplied the correct TOTP code at that instant? And so this is the key insight of MFKDF, is that you can use a little bit of fairly simple cryptography to accomplish this. And unfortunately, I don't have nearly enough time to go into the underlying cryptography. But there's basically a key feedback mechanism that allows the key derivation function to store secrets ephemerally in the function itself. What's essentially happening is that every time a user derives a key with multi-factor key derivation, they're setting up the next login attempt already, so that the next login attempt will succeed if and only if the correct factors are provided. And we implemented these factor constructions for a wide variety of commonly used factors, including HOTP and TOTP, as well as YubiKeys, all kinds of out-of-band authentication factors, and even intrinsic factors like biometrics. And so a user can then use all of their authentication factors together. And now an interesting thing that Connor mentioned is that password-based key derivation functions should be slow. They're intentionally slow to defeat brute force attacks. And the interesting thing about MFKDF is that the intentional computational inefficiency is on top of the product of all of the factors. So in other words, it's not like I can brute force your password and then I can brute force your TOTP and now I have your key, right? I would have to brute force all the possible combinations of all of your factors, which gives me an exponential improvement in the brute force resistance of this key. All right, so that answers the first question. We can, in fact, incorporate all of the authentication factors into the key derivation function. But another question that we might have, in fact, this is a question with password-based key derivation in general, is what do you do if the user forgets the password? After all, the password now is their key, and so presumably if they lose the password, they have lost their key. They've lost the ability to access all of their data. And the way that password management services address this in practice today is either A, you're out of luck. If you lose your password, all your data is gone. Or B, we're going to implement some sort of master key in our system that can unlock any user accounts, and this creates a central point of failure. In fact, it largely defeats the point of PBKDFs in general. And so to address this, we introduced a threshold version of the multi-factor key derivation function that actually allows users, developers, to set up keys with more factors than are actually needed. So you may, for example, set up a key with a password, a TOTP code, and a recovery code, and during normal login, you would just use the first two factors. But you set it up as a 2 of 3 threshold solution using Shamir secret sharing behind the scenes, where let's say the user forgets their password. Now they can use the other 2 factors and still derive the same key. Or if they forget the TOTP code, same deal. So you can use any 2 of 3 to derive the key. This now creates a secure client-side recovery mechanism based on some threshold of the factors that doesn't introduce any central point of failure. In fact, we can go one step further with this, which is the idea of, now I have this threshold multi-factor key derivation. What if I actually use a derived key as one of my factors for another multi-factor key derivation? Well, we call this key stacking, and this enables a really powerful capability, which is called policy enforcement. And what this actually allows you to do with MFKDF is to create sort of logical circuits that combine your authentication factors in arbitrarily complex ways. So you can use these circuits to define an authentication policy that specifies exactly which combinations of factors should be allowable to derive your key. And instead of being enforced by the software, by the authentication server, this complex authentication policy is now directly cryptographically enforced, such that you can only derive the key if you present some combination of factors that satisfies your policy. So this would even allow things like risk-based authentication that was discussed earlier to now be implemented in a purely cryptographic way. We did some performance benchmarking to show that the overhead here is really minimal when compared to password-based key derivation. And you have to keep in mind, again, that key derivation functions are supposed to be at least a little bit slow to make them hard to brute force. And so with that in mind, the additional few milliseconds of switching PBKDF-based system to MFKDF has really negligible impact to the end user. So I want to encourage all of you to take a look at mfkdf.com. We've tried to make it as easy as possible to implement in a wide variety of systems. This is something that should be a drop-in solution for any system that uses PBKDF2 right now. You can replace it with MFKDF and have a working system that now uses all of your users' authentication factors in the key derivation process. Also, just for fun, we also got PBKDF2 and redirected it to MFKDF so that no one gets confused about which one to use moving forward. So you can also check it out that way. And we've also done a couple of demos here. One of the demos that we did is actually, based on the example I introduced at the start, building a password management service based entirely on MFKDF. And we showed that, in fact, you can have a system where all of the user stored passwords are encrypted with multiple authentication factors. And we also had a really interesting cryptocurrency wallet implementation where a user basically can manage a cryptocurrency wallet key using multi-factor key derivation instead of storing or moving the key manually. And this basically results in a system that looks exactly like a centralized exchange, something like Coinbase, but in fact is totally decentralized because you're just deriving the key on the client side. And so the point is that there are both new and existing applications that can really benefit from this technology. And speaking of existing applications, PBKDF2 is pretty widely used. So if you connected to the Wi-Fi network here, you probably used it in the wireless authentication protocol. If you have an iOS or Windows device, you're using PBKDF2 for disk encryption. And as I mentioned, MFKDF sort of is a drop-in solution for these things. So we're really imagining a situation where now you can have your wireless network support multi-factor authentication cryptographically. Or when you log into your laptop can also support multi-factor authenticated disk encryption cryptographically. So imagine all the places PBKDF2 is used right now, and now having the flexibility to support arbitrary combinations of commonly used authentication factors as part of those systems. So in summary, MFKDF provides factor constructions to derive key material from a wide variety of popular authentication factors. It does this in a way that provides an exponential improvement in security and brute force resistance. It also provides a client-side recovery mechanism to solve the recovery problem that exists with a lot of PBKDF-based systems. And on top of this has a policy enforcement layer that allows you to use logical circuits to construct arbitrarily specific key derivation policies. It does this while having minimal overhead over PBKDFs and can be used in a wide variety of new and existing applications. So that's all I have for you. Happy to take any questions. Thank you.